Implicit differentiation. Our objectives today is know the difference between explicit differentiation and implicit differentiation. Implicit differentiate with rules of differentiation to find tangent lines to curves. We're going to first start with a conic section. We'll start with x squared plus y squared equals 25. Now, if you recall this from algebra class, you know that this is actually not a function. You know this is a curve. So curves are not necessarily functions. Curves don't always satisfy the property for every x there's exactly one y. So when we write this circle of radius 5, we know this is clearly not a function. You know, at x equals 0, there's two y values. And so you know that this cannot possibly be a function. However, if you solve for y and you make sure that the two different y's has an exponent of 1, then we actually have two distinct functions. Notice the top half of a semicircle is a function and the bottom half of a semicircle is a function. So when we talk about a function explicitly, it really means that we have a y, which really stands for a function of x, and that y has an exponent of 1. So notice up here, if you have an exponent of 2 on the y, then this is actually an implicit equation when we talk about functions. Down here though, however, you have an exponent of 1. Why don't we call that y sub 1? Y sub 1 will have an exponent of 1. And this one here, y sub 2, is a function. And it has a exponent of 1 as well. So it's not y squared. It's actually just a y with an exponent of 1. So explicit differentiation, let's go over this again. You need a y value or a function with an exponent of 1, and then the independent variable is always on the right-hand side of that function notation. So if you explicit differentiate, then you just take the derivative with respect to x. And so in many ways, you have been explicitly you have been explicitly differentiating for many practice problems. So for this particular curve, it's broken into two distinct functions, and then we explicit differentiate each of them. So here's case 2. It's a function of x. Y has an exponent of 1. We'll go ahead and differentiate this. And this process is called explicit differentiate. Now, it'd be nice to know if there is a possibility to differentiate curves without having to solve the functions explicitly. For some functions, it will be very difficult to solve for y and make sure that y has an exponent of 1. So, is there a process where we could find, the slope of a tangent line to a curve? And the answer is yes. We actually call this implicit differentiation. Now, you got to remember that y is just some function of x. If y is some function of x, then we could actually implicit differentiate many different equations. So our goal here is to find an equation of the tangent line, tangent to this circle of radius 5, at a particular ordered pair. Now this is a very rough sketch. And the ordered pair is -3, -4. So we're down here somewhere, and we're in quadrant 3. Now our goal is to find the equation of this tangent line. Okay, we're wondering what is the equation of this tangent line. We do know that the slope of this tangent line appears to be negative. So that is good intuition. Okay, so if you know your algebra, you gain some intuition for calculus. Always helps. Now, in order to implicit differentiate, you just got to remember y is some function of x. So if y is some function of x, we could see that y squared is now a composition. And that composition is defined to be g composed with y of x. So then you have y of x quantity squared. And this could be your u sub, but your u sub is just a renaming of y. If you apply the chain rule, or Leibniz notation, we know that the derivative g with respect to x is simply the chain rule. The first rate is the derivative g with respect to y times the derivative y with respect to x. So if you ever have an exponent here that's not 1, you just got to remember this chain rule idea. Leibniz notation is preferred. It tells a story, and it's much easier to change variables depending on the application of study. So why don't we go ahead and do this? I'll illustrate an example. We're going to go ahead and take that equation, and we're going to differentiate with respect to x, knowing that y is a function of x. Now, differentiate x squared with respect to x, you get 2x. Now the goal is to differentiate y squared with respect to x. That means we have to differentiate g with respect to y. So that would be 2y times the derivative of y with respect to x. All I did was this substitution right here. And you end up getting that derivative for that particular expression. Now, if you differentiate 25 with respect to x, not a problem. That would just get you 0. Now, the goal here is to find the slope of the tangent line. That means we have to solve for dy dx. And there it is. Now we're going to change procedures. We want to find the slope of the tangent line at the point of tangency. So it's -3 over, I'm sorry, it's the opposite of -3 over -4. So we end up getting -3/4. I'm going to change the procedure again. We're trying to find the equation of that tangent line. So why don't we use our point slope form and then work ourselves to point intercept form or slope intercept form. Ordered pair was -3, -4. Slope of the tangent line was -3/4. And there is the equation of the tangent line with a negative slope as expected from your algebra experience.